the pulse rates of 160 randomly selected adult males vary from a low of 39 beats per minute to a high of 119 beats per minute. Find the minimum sample size required to estimate the mean pulse rate of adult males. Assume that we want 90% confidence that the sample mean is within 4 beats per minute of the population mean. First, we use Z-stat or T-stat. Do we know the population standard deviation? We don't. We're going to estimate it with a range rule of thumb. Go to T-stat. One sample, width, and sample size. We have 90% confidence level. Our standard deviation is our range rule of thumb. That's equal to the range divided by 4. And the range is equal to high minus low divided by 4. In our case, it is 119. Low is 39. Divided by 4 is 80 over 4, which is 20. That gives us our standard deviation. The width, we want the sample to be within 4 beats per minute of the population mean. If I drew a picture, here's the sample mean, and now I have to find my width. Assume that we want 90% confidence that the sample mean is within 4 beats per minute of the population mean. We only have the sample, but we want X bar minus 4 and X bar plus 4. The width is from here to here. It's going to be 4 from here to here, and it's going to be 4 from there to there. Our total width is 8. Compute. 70 should be the right answer. Assume that our sigma is equal to 12.3 beats per minute based on the value S. We're going to change our standard deviation to 12.3. N is now 28. Perfect. Compare the results from part A and B. The result from part A is definitely larger than the result from part B. The result from part B is likely to be better because it uses a better estimate of sigma. Assume that the sigma, which is our population standard deviation, is 12.3. That should give us a better estimate. Let's see. An IQ test is designed so that the mean is 100 and the standard deviation is 18 for the population of normal adults. Find the sample size necessary to estimate the mean IQ score of statistics students such that it can be said with 90% confidence that the sample mean is within 4 IQ points of the true mean. Assume that sigma equals 18 and determine the required sample size with technology. Then determine if it is reasonable sample size for a real-world calculation. We know sigma, and when we know sigma, we can use Z-stat. And we know IQ scores are normally distributed. Let's go to stat, and we can use Z-stat for this. One sample, and this is width. And I'm going to get the sample size. This is 90% confidence level. My standard deviation was given to me as 18. My width is 4 in each direction. My width is 8, which gives me a sample size of 55. Would it be reasonable to sample this number of students? Sure. This number of IQ test scores is a fairly small number. We can find 55 people. The ages of a group of 122 randomly selected adult female have a standard deviation of 17.3. This is a group of 122. It is not the standard deviation of the population, it's the standard deviation of the sample. Assume that the ages of female statistics students have less variation than ages of female in the general population. Sigma equals 17.3 years for the sample size calculation. How many female statistics students' ages must be obtained in order to estimate the mean age of all female statistics students? We want a 99% confidence that the sample mean is within 1/2 of a year of the population mean. First, let's put our standard deviation of 17.3 that I was given. The last thing is going to give me my width. If we want it to be within 1/2 a year of the population mean, that means a 1/2 a year in one direction, or 6 months in one direction, 6 months in the other direction, which gives us 1 full year. I need 7,944 students. Does it seem reasonable to assume that the ages of female statistics students have less variation than ages of females in the general population? I would say probably yes, because statistics students are typically younger than people in the general population. Yes, because they're older. No. In a test of the effectiveness of garlic for lowering cholesterol, 45 subjects were treated with garlic in a processed tablet form. Cholesterol levels were measured before and after the treatment. The changes before to after in their levels of LDL cholesterol have a mean of 3.6 and a standard deviation of 15.2. Construct a 99% confidence interval estimate of the mean net change in LDL cholesterol after the garlic treatment. What does the confidence interval suggest about the effectiveness of garlic? One step at a time. One sample with summary, and we put in our summary values. We have mean is 3.6, standard deviation 15.2, sample size was 45, confidence is 99. We can show the critical value. Here's our values. Let's put them in and see what we get. To 2 decimal places, that is, check our answer. Perfect. What does the confidence interval suggest about the effectiveness of the treatment? We have a confidence level of 99%, and we know our values. Let's read them. The confidence interval limits do not contain 0. Well, between a negative and a positive, that mu's got to get to 0. That's not true. The confidence interval limits contain 0, good, suggesting that the garlic treatment did affect the LDL cholesterol levels. Confidence interval limits contain 0, suggesting that the garlic treatment did not affect the LDL. We have this confidence interval, and inside that interval, there's a 0. Nothing may have changed at all. If we're saying that it's the before number minus the after number, and that becomes 0, well, then this didn't help at all. A food safety guideline is that the mercury in fish should be below 1 part per million ppm. Listed below are the amounts of mercury per million found in tuna sushi sampled at different stores in a major city. Construct a 95% confidence interval estimate of the mean amount of mercury in the population. Does it appear there's too much mercury in tuna sushi? What do we have to do? We have to check our requirements first. Here's our data. Let's open Statcrunch with new data. For our requirements, we know It has to be below 1 part per million. It really doesn't tell me anything, does it? How about if we graph QQ plot mercury, and I like putting the correlation statistic in there. It tells me how close I am to 1, and this looks good. I'm very close to 1. I can consider this normally distributed. This is the amounts of mercury found in the tuna, and I need to construct a 95% confidence interval estimate of the mean amount of mercury. Are we going to need a T or a Z? We're going to need a T-score because we did say it's normally distributed, but we don't have very much data. We're going to use our T calculator. One sample with data. There's my data. Confidence interval of 95%. I can see, is it actually normally distributed? What is the confidence interval estimate of the population of mu? I want my lower limit to 3 decimal places, and my upper limit is going to round up to 9. Does it appear that there's too much mercury in tuna sushi? We can see this 1.25 is over, which means it's dangerous. No, because it is not possible that the mean is greater than 1 part per million. That's not true, because it is possible that the mean is greater than 1 part per million. Confidence interval contains a mean that is greater than 1. Yes, because it is possible that the mean is greater than 1 part per million. Also, at least one of the sample values exceeds 1 part per million, so at least some of the fish have too much mercury. No, because it is possible that the mean is not greater than 1 part per million. Also, at least one of the sample data values is less than 1 part per million, so at least some of the fish are safe. I only have one that's above this 1.25. Does it appear that there is too much mercury in tuna sushi? Yes, because it is possible that the mean is not greater than 1 part per million. Also, at least one of the sample values exceeds 1 part per million. At least some of the fish have too much mercury. It is possible that the mean is greater than 1. It can go all the way up to, this is our upper limit. It's got to be that. Refer to the accompanying data set and construct a 90% confidence interval estimate of the mean pulse rate of adult females. Then do the same for adult males. Compare the results. We have males and females. I'm going to open Statcrunch with the data that they're giving me. Construct a 90% confidence interval of the mean pulse rate for adult females. Again, let's look and see if we have the requirements for a T or a Z score. We'll do females first. Let's graph the QQ plot for females and see if it's normally distributed. Looks beautiful. We can even put our correlation coefficient, almost 1, perfect. I now know it's normally distributed, and I have 40 values. It has to be a T-score because we don't know the standard deviation. That's what we want to look for. Do we know the standard deviation? And we do not. We have to do a T-stat. One sample. And we're using females. 90%, 0.9 or 0.90. We can put that plot, hit compute, and we're given the lower limit to 1 decimal place, 72.8, and our upper limit, 79.8. Construct a 90% confidence interval of the mean weight for adult males. Similar, just we're going to go up here, options, edit, and instead of females, we're going to pick males. Other than that, everything is the same. It's very normally distributed. We have our lower limit to 1 decimal place, 64, and our upper, 70.6. Compare the results. The confidence intervals do not overlap. This goes from 64 to 70.7. They do not overlap. That's true. It appears that adult females have a higher mean pulse rate than adult males. Here's females, here's males. That's true. The confidence intervals overlap? No. The confidence intervals, they do not overlap. It appears that there is no difference in mean pulse rates between adult females and adult males. That's not true. Since they don't overlap, there's quite a bit of difference. I'm going to stick with A. That's the end of this portion of the lecture. Thank you for watching.